Okay, now let's talk about the forces present in springs, elastic forces, elasticity, and stress and strain. So let's say that we have a spring attached to a wall over here, and it has this handle here. And let's say we apply a force to this handle and we stretch the spring out. So it had some original length x here. This was its original length, and then we stretch it out some delta x. And so we've applied a force. This is the force of the hand on the spring. So the force of the hand on the spring here is off to the right. And of course, this force of the spring exerts on the hand is going to be off to the left. And I should have drawn these the same magnitude. These would be balanced out. And you may know from experience that if you want to stretch the spring farther, then you need to apply a greater and greater force. The same is true for compression. If you want to compress a spring, the more you want to compress it, the more force you are going to need for that. This is the same way that like a scale, a spring scale works. Maybe if you go to the grocery store and you're buying some vegetables or something, you may attach a basket here that would apply a force. Imagine this is vertical, and it would apply a force this direction. This would be the force of your produce on your spring, right? And then the force the spring exerts back on the produce would be back like this, and they would balance out. So we can measure this force through this displacement. And the way we do this is we say that the force a spring exerts on an object is directly proportional to the displacement. This is actually something called Hooke's law. So Hooke's law. What Hooke's law says is that the force the spring exerts on an object is negative k times the change in length here, really, I guess sometimes it's better written as just a delta x. So the force the spring exerts is equal to negative k times delta x. All this negative here is this is just saying that the force the spring exerts, it would be opposite of the displacement. So if this displaces to the right, then the spring force is to the left. This is all it is. The magnitude of it, oftentimes we'll just want the magnitude, it'll just be k delta x. If I compress a spring, clearly my delta x would have been in this way. It's like I compress it here. This is my delta x. And so then the force the spring exerts on the object would have been off in this direction, opposite of that displacement. That's all the negative is. The delta x is actually the displacement. If I want to increase the force, then I can increase the displacement. Or if I want to increase the displacement, I need to increase the force. And this value k, this is what we call the spring constant. The spring constant itself is always positive. This negative gives us the direction. So k is the spring constant. Or sometimes it's called the force constant as well. And so what this is just a constant of proportionality. We said the spring force is directly proportional to the displacement. This k is just our constant of proportionality. And it depends on the spring itself, right? So it depends on the material the spring is made out of. If I make a spring out of steel, it's going to have a much higher spring constant than if I make it out of gold, right? Gold is very malleable. It also depends on how tightly coiled the spring is, okay, and the thickness of the coils, etc. So this depends on the spring itself. So we need to be given k, or maybe we're given the displacement and the force, and we can find k. But the ones that you see, these spring scales that you see in the grocery store, they know the spring constant, and these are calibrated so that way a certain displacement here correlates to a certain weight. Okay, so k is a spring constant, which is a property of the spring itself. And so let's take a look here. Not everything follows Hooke's law. There's actually only a region in which Hooke's law is obeyed, and this is just the first part of what we call the elastic region. So if we look at, here is our change in length, and here is our force. Then when this is linear, when we plot the change in length versus the force, when there's a linear relationship between these, after all, if we look at the slope, delta L over F, this would be equal to, just rearranging this equation, or I could have said delta X over F. This would be equal to, just looking at this would be equal to the spring constant. It is linear. So in the region that there's a linear relationship between the displacement and the force, Hooke's law is obeyed. Beyond that, the relationship becomes nonlinear. So if we stretch it too far, there gets to be a nonlinear relationship, and we see that the greater the force isn't displacing it quite as much. So this Hooke's law is no longer obeyed. In this region over here, we no longer have Hooke's law obeyed. However, it is still in our elastic region, and elastic will become more important later, but what we mean by elastic is that if we stretch it out and then we let go, it returns back to the same length that it was before, right? So exactly what you would think when you think of elastic. If you stretch it out, you let go, it snaps back to where it was. If you compress it, let go, it bounces back to where it was. After we get outside of the elastic region, we get into what's called the plastic region. If you stretch a spring too far, then it'll be permanently deformed. It won't snap back. And so this is getting beyond the elastic region. All this is called the plastic region. And then after this, then eventually it just snaps and breaks. But anyways, the important thing here is that just Hooke's law is obeyed in this first little area where the displacement is directly proportional to the force. But of course, we were just talking about like a spring and just a force here, right? This also is an idea of elasticity, and this property of materials to stretch and compress and be elastic extends beyond just springs. So we can also just have like a steel rod that will stretch when we apply a force or compress when we apply a force. And so instead of just looking at a force, let's expand it a little bit. Let's expand this to like a steel rod. So if I had a really skinny steel rod and I apply a force to it, then I might expect some stretching. But if I have a really thick steel rod and I apply that same little force, I might not expect quite the same amount of stretching, because this force is spread out over such a large area here, and this one over such a small area. So the first thing we need to do is actually, instead of just talking about a force, we need to normalize it per the area. And so this is something we call the stress. So stress is defined to be a force, and it's actually a perpendicular force, perpendicular to the surface divided by the area. And so this one, we can see here, this would have a greater stress. If these are the same forces, there's a much greater stress acting on the skinny rod than there is this thick one, and we would expect the skinny rod to be stretched much more, right? So this is the first thing we need to do, is we need to define stress. Force will be in newtons, area will be in meters squared, and so this is newtons per meter squared. We also call this a Pascal. These are the same units as pressure, which we'll see in later chapters as well. Pascal, PA. So this is stress. We also need to talk about relative stretching. If we have a short, let's say we have a rod here, and it's short, we apply a force here to stretch it out, and then we have a long rod, and we apply the same force to stretch it. Which one would we expect to stretch more? Well, if they're the same material, we would expect just this much. This one, just this length of this rod would stretch as much as this one. But there are several lengths of this rod in here, right? It's maybe 4 times as long, 5 times as long here. So 5 times as long, we might expect it to stretch 5 times as far. Okay, so we need to be careful and say, well, how long is this spring or this rod before we say how much does it stretch. If we stretch out a piece of wire that's a mile long and we apply a force to it, we'd expect it to stretch a couple feet maybe, versus one that's only an inch long and we apply a force, we might not even notice how much it's stretched. So we need a relative measure of the stretching as well, and this is what we call strain. So strain is a ratio of the change in length to the original length. Okay, this is unitless. This would be in meters, this would be in meters, and so strain is a unitless value. We could just express it as a percent or a ratio. Okay, so the strain is the relative change in length. Okay, so let's say I have here, it's just a figure. I have some delta L divided by L naught. This is my strain, and then I have some force here divided by this area. I have stress. Okay, so same thing as over here. This would be a stretching. This would be a compression. Same as what we had with the spring. And so just labeling these in Hooke's law, where we had F is equal to Kx. There's a negative here. I'm just going to forget about this negative sign because it only indicates the direction. So the magnitude of the spring force would be the spring constant times x. But instead of a force, now we are going to talk about a stress. And instead of a displacement, we're going to talk about a displacement per original length. And so we have here the perpendicular force divided by area would be equal to some spring constant divided by a ratio of our change in length to original length, or stress is equal to some constant times the strain. Since this is our spring constant, really, we then actually replace this constant with something more general, and we replace this with a y. So this y stands for Young's modulus. So Young's modulus of elasticity. And so what this becomes is that the perpendicular force per area is equal to Young's modulus times the change in length divided by the original length. And so this is basically Hooke's law rewritten for like a stretching metal wires or something like that. All we did is we said, well, let's do force over area and let's do a ratio of the change in length, and we changed the spring constant to Young's modulus of elasticity, given in your textbook there. So Young's modulus is usually given just like the spring constant. It's a property of the metal or whatever we're stretching there. Sometimes we could rearrange this however we want. We could say then that the change in length, let's say I apply a force to something, we could simply say the change in length of it would be equal to the perpendicular force times the original length divided by the cross-sectional area times Young's modulus. If we wanted to, we could rearrange this any way we want. But basically we have, this is relationship between stress and strain and elastic deformation, which comes from Hooke's law.